Hello guys, in this video we're going to discuss about linear regression. So let me take an example data points so that we'll be understanding the model much more clear and much more better way. So we had x and y features, two features. So we need to predict y based on x. So x is a feature and y is a predicting variable. It means x is independent variable and y is dependent on x. That's the basic assumptions, and there are even a lot more assumptions which we'll be discussing at end of our video. So we had x and y, and I had plotted the graph. Let me give you the what is linear regression. Well, we need to predict yi based on xi values, that's the observation features, and we'll be having a slope to it and where it intercepts to y. So based by injecting the x values, we will be predicting yi. So this is the basic idea. So we need to draw a line. So we cannot draw randomly. We need to use gradient descent for finding the better weights of the slope and the intercept. So if you see in the linear regression model, we had 4 data points as per the table. So we need to build a model. Let's consider this is a random line that we draw. So we need to predict the model in such a way that the errors will be reduced. So let me take to what are the errors. So if you see that at x1, this is x1, this is x2, and x3, and x4. We had x1, x2, x3. You can see that 1, 2.5, 3, and 4. And we had y's. These are the y's. Let me draw with the blue ones. This is y1. This is y2. This is y3. And this is y4. So let me now, what are the values we can predict based on x? If you see that x touches the intercept here, so this will be my y at x1 we had predicted y1 based on the expression. At x2, this x2 will touches the line here. So if we draw the line, it will be y2 hat, while x3 will touches my line here. So this is my predicted one, will be my y3 hat. The x4 touches my line here. So where we had the already my y4 is on the actual value, it's there. So y4 hat. Now we want to see the difference in between the actual one and predicted one. Those are the errors. So let me take the white one. Yep. So let me calculate the error one at, for first observation. We call it as error one, or we can call that residual first residual. So we had last function one, and we need to predict the actual one. That means y1 minus y2 y1 hat. So this is the actual one and this is the predicted one. So if both are equal, we'll be getting 0. It means our model is predicting correct. Since at here, when I talk about y1 is 4. So 4 minus, that's y1 hat is also 4. You can see that it's predicted 4. So 4, it will be 0. Now let's talk about the error 2, or second residual, or last function 2 equal to y2 minus y2 hat. It will be, when I talk about what's the y2 observation, it's 5. So 5 minus what's the y2 hat. So you can see that this is y2 hat in between 5.5 to 5. It means we can say that 5.25. So let me write it down here. So it's 5.25. It means minus 0.25. So now let's talk about error 3 equal to third residual equal to loss function 3 equal to y3 minus y3 hat equal to what's y3 observation? Well, if you see the values, then 6 is y3. So 6 minus what's the observation of y3? You can see that at x3, it touches here. This is the predicted one. So it's in between. Let me erase this. It is in between 5.5 to 6, and you will be getting clear picture. So I'm gonna write it's y3 and this is y3 hat, right? It's in between 5.5 to 6, so it's gonna be 5.75. So it's the y3 hat is 5.75, which if you do the minus, then it's 0.25. So now we will be calculating for E4, error 4 or residual 4 or LF4 equal to Y4 minus Y4 hat. So if you see the observation, the Y4, it means 1, 2, 3, 4, it's 6.5. So 6.5 minus, let me see the dictated one. This is X4, it touches the line here. So it means line is still going like this. So it touches here, it means it is also 6.5. Y hat and Y4 were on the same point. So it is 6.5. Then if you minus it will be 0. So now I want total error. So if we do all sum, then it's gonna be 0 minus 0.25 plus 0.25. Both will be cancelled. So my total error will be 0. But actually, if you see the graph, we had the error. So let me erase it and show you clearly. Yep. So you can see that this is the difference. So this is the difference. Here you can see that this is the difference. There is the error. There is the error. But since we are adding directly, they're getting cancelled, the opposite and positives. So what we do, we used to square them and add them. So what we are doing, we are adding error 1 plus error 2 plus error 3 plus error 4. So we are squaring them and adding so that they won't get cancelled. So if you want to write in one statement, then summation I equal to 1 to 4 E of I whole square. What is error? Actual value minus predicted value whole square. Sum of I is equals to 1 to n, where n is equals to 4. This is the formula. So keep in mind, this is very important formula. We has had the residual formula. We can call it as sum of squares of residuals. Let me lay it down very clearly for you. So sum, we are summing it. Square, we are squaring it. Residuals. What's the residuals? As I said in the top of the video, R1. This is the residual one, stuff like that. We are summing the and squaring the residuals. So it's summation I equal to 1 to n y of I minus y of I whole at whole square. So we had yi, which is the actual values from the data. What about the y I had? That's the predicted value. It is the line. What's it? It is the line we drawn here. So this line is the y I had that's predicting. You can see that each time it crosses that, it predicted here at x2 predicted y2 hat. Here at x1 it predicted y1 hat. X3 it will be predicting y3 hat. Here at x4 it is predicting x4 hat. So it is a line expression. So it is equal to mx plus c, you can consider. So if you wanted to if write it down in even detail, I is equals to 1 to n whole of yi, which is the actual value, minus mxi for each value of xi. What is the xi? This is each value of x from the table. Okay, so minus. So since we are applying this equation here, so the minus will be multiplied for both the variables, right? So c whole square. So this is called as cost function, or you can also call it as sum of squares of residuals, or the as we are summing total error residual, or even it is also called as j, which is cost function. So now you will be understanding what's the difference in between the cost function and loss function. When I talk about the loss, it means we are calculating for each and every individual, loss 1, loss 2, loss 3. But the cost function is we are calculating summing all of them. Like you can write like this: cost function equal to sum of loss function of individual values where I is equals to n, or sum of squares of residuals, or the equation, like this is the even equation. So remember this, we'll be using this equation in our gradient descent in the next video to solve it and to get the better optimum values, because we need to minimize this. This is the error, right? For the actual one and the predicted one. This is the line and these are the actual values, and we're predicting a better fit line, so that we need to minimize this error. Now let's talk about uh, assumptions. Why we need to make some assumptions? Well, while building linear regression itself, we are assuming this or parsing. Like I mean, the model we are building, we assume that the data has processing all these statements, and I will be explaining each and every assumptions because that where we will be getting that how these assumptions are needed and important for building linear regression. First, let me take about the important ones, linearity. We assume that the data is spread linearly. Like if we see that there is a x variable and y variable, the data is spread linearly so that if we have a predicted line, then it is best fit. For example, if the data points are fit like this, not in a linear fashion, then if you fit a line, no matter which line you fit, they are not, you're getting too much of error. And when you make any predictions from this model, it shows a lot of errors. So you're making wrong predictions, and that may leads to wrong guidance. So make sure that the data is spread evenly or linearly. Now let's talk about autocorrelation. The data, when we wanted to build a linear regression, the data should not be autocorrelation. Why? Because if you see autocorrelation, it means if you have the data points, each and every observation should be independent with each other. So there is no relation or a dependent the second observation based on first observation. Let me tell you what is autocorrelation observation. If we have the sensor data, like you will be reporting each and every hour. For example, if you have a temperature sensor data which is coming to your database, this is early morning, this is second observation is at afternoon, third observation is at evening, and fourth observation is night. So there is a relation, right? It's morning and afternoon little hot, and evening it may be little low temperature, and night you may report low temperature, but there is a relation time, or it may be the dates in some cases if you talk about the stock markets or many other things. So it should be independent. For example, if you consider weights and heights, so each and every individual person height and weight is independent with respect to each other. That will be the best case. This we can call it as this weights and height, we can call it as no autocorrelation. When you talk about the stock market or sensor data, that's where no correlation. It means they are autocorrelated. So each and every observation is related to each other. Now let's talk about the third one, which is homoscedasticity. It means there should be no heteroscedasticity. It means it should be constant variance. It means let me draw you the x and y. So this is the feature and y is the predicted variable. So if you think that the data should be spread constant in the first one, like linearly, and it should not increase. If the x value is increasing, if you see in the x-axis, if the x value is increases, the data point spread is increases. So since this is called heteroscedasticity, so it should be homoscedasticity. So we need to use some of the technique to make the data normal. For example, if you draw this data in the x-axis histogram, it's gonna be right skewed. Sorry, it's gonna be left skewed. So what we do, we apply cube for it, or we're gonna apply log to it, or we're gonna square it to make it normally distribution. That's one of the key important thing that you need to remember. Let's talk about the fourth one, which is normality error. So we had understood what is error. That's the difference. So for each x value, we had the difference in between the actual value and the predicted value. So if you draw the graph, it should be not the error value should be equally distributed. Like let me with in this example we had discussed about we had four observations that x1, x2, x3, x4. What's the value of x1 and x2? Like you can see that the value of x1, x2, x3, x4 are 1, 2.5, 3, and 4. So 1, 2.5, 3, and 4. Let me get the error values. What the error values? If you see here, it's 0 for x1, minus 0.25 for x2, 0.25 for x3, and 0. Okay, let me write it down here. You will be having clear picture. These are the error values. It's 0, minus 0.25, 0.25 for x3, and 0. So we had this graph. These are the x values from the data. This is the error. So if you draw the graph, the middle will be 0. We had one point to the left side. Let's consider this may be 0.25. minus, and this is plus 0.25. We had two values, so the more is here and less is like this. Since we had only four observations, the graph looks like this, but if there are too many observations, then you need to get this normal curve, and the zero will be in between. Then your data is perfect. Like, I mean, your model is passing one of the assumptions, so your model is working fine. Now let's talk about no multi-correlation. What do you mean by no multi-correlation? In this example, we had only considered one feature, that is X, but in real case, there may be multiple features. So uh, let me consider, like, there is X1 feature, and there is X2 feature, and X3 feature, and we had Y, that's a predicting variable. So x1 should not depend on x2 or x3, and x2 should not be dependent on x1 or x3. X3 should not depend on x1, x2. How do you find it? Basically, we used to take the correlation of these variables, and we should see that all three variables are not related with each other. It means they are not dependent on each other, so that we can predict y. If they are dependent, then we need to use few other analysis. Like, for example, if x1 and x2 are highly correlated, it means the correlation was 0.9, or you can consider negative 0.9. It means, what do you mean by 0.9 positive? It means if x1 is increasing, then x2 is increasing. If it's negative, then x2 and x1, if x1 is increasing, x2 is decreasing, it's opposite, that's it. So if they are highly correlated, then we can use PCA to club together and use them. Why they should not be multi-correlated? Since, for example, we're predicting y, it means if we have the expression that yi equal to x1 w1 plus x2 w2 plus x3 w3 plus there may be constant. So if you want to interpret this, if it means for every 1 unit increase in x1, the y will be increasing by y1 by keeping all other variables constant. But since the x1 and x2 are highly correlated, it means if x1 is increasing, x2 is also increasing. So which means it's overcoming the basic ideology of our linear regression, so that we need to have the features which are not correlated. It means which are not dependent on each other. That's the main thing that we need to remember. And these are the assumptions. So make sure to have idea about this J function, which is cost function of the linear regression. We'll be using this cost function in our next gradient descent model to predict this M and Y, and seeing how we can optimize, how we can get better values so that we can minimize the error. It means how we can draw a better line, how we can get the best fit for this data to minimize the errors. So yeah, see you in the next video.